5.10, your course is 350 true, and your speed is 15 knots. Let me sit, actually. You can go over my shoulder or whatever. Okay. You probably want like a forward view of it, so you know what's happening. Okay. Our course is 350 true, and our speed is 15 knots. Okay, so that means, let's see. At 9:10, a contact bears 10 true, range 27,000 yards. At 9:20, the contact bears 21,000 yards. So our scale that we're going to choose for that one is 3 to 1. The reason for that is because we have 27,000 and 21,000 will be contained in 3 to 1, meaning that this 1 to 10 scale will go actually from 0 to 30,000 yards. So I circle that 3 to 1 scale to indicate what I'm doing. Now our course is 350 true, and our speed is 15 knots. So 1, 2, 3 notches up. So and it's on the 350 line. So this is our 1, 2, 3, 350. That is our, let me see this, ER vector, which indicates our own course and speed. ER. At 0, 9, 10, a contact bears 10 true, range 20,000 yards. So we go on the 3 to 1 scale, 27,000 yards, which is, I know it's going to be 9, but I'm just doing this to show you how you would do this. So how I would do this is I would count up up to this notch here, which is 9, but as you will see, look, it goes right over the 9. So, oh wait, sorry, 9 at the 10 degrees. So this is 0, 9, 10. This is our their bearing from us. Then at 9:20, 10 minutes later, the same contact bears 0, 0, 0, 0 true, range 21,000 yards. So by the same token, we're going to be putting this at the 7. If you were to measure this out right here, it would go right there to the 7. So this is 0, 9, 20. Okay, so let's get the course and speed of the contact first. Okay, so I'm going to draw a dotted line here. I always draw a dotted line because that will help me differentiate between my vectors and my relative bearing lines. So this line is basically, this line here indicates the bearing of our contact from us. So at 10 minutes later he'd be here, etc. So course and speed of the contact. So we know that the contact takes 10 minutes to get from here to here. So how far is that distance? That's what we need to find out. That distance is on the 3 to 1 scale. This is where the 3 to 1 scale becomes important. Okay, so I'm using the bottom one. So it crosses right here, which is at 7,000 yards. So this is from here to here is 7,000 yards. So I mark a line right here at 7,000. Then I mark a line at time in minutes 10. So we have there, there. Where those two cross, 2 points make a line. I just use that. From there, I get their speed to be. That crosses there, that crosses there. Approximately 20 knots. I think it should be 21 knots. Because yeah, it's 21 knots. Make sure your lines go through there, because just a slight deviation can cause a whole knot degree. But usually it's like within plus or minus 3 knots. That's how we were always graded in that class. But 21 knots. So that's his course. So let's go to 21 knots, or that's his speed, I'm sorry. 21 knots, dang it. Dang it. There we go. 21 knots. So then we also have his speed, or his relative motion. So what we do is we get his, let me go this way. So we get basically that parallel line that I drew before, that's his relative motion to us. So we bring that over here, and then we draw a line of magnitude 20 knots from there to get his course and speed. So it's going to be actually right here. I'm just trying to be right there. So the reason why I drew it that way is because his direction is that way. So if this were 910 and that were 920, if he were moving that way, then I would have gone up. But as it stands, this is our RM, standing for relative motion. So then finally, his course and speed is the EM vector, which is going to be of direction or course whatever this is, 264.5 true, and the magnitude of the speed on the 5-to-1 scale is less than 21 knots, which is going to be,
and so you always measure it there?
on the 5-to-1 scale, 16 knots. So he is moving at 16 knots. So you would write that up here, 16 knots, 270 or 264.5 true. CPA. So this is basically, to find the CPA, all we're doing is finding a 9 wherever, like the closest point geometrically, the closest point from the center to this line is when we have a 90-degree angle, right? So what I'm going to do is take his bearing, so his line of relative motion. All I want is the angle that's 90 degrees away from that. So his line of relative motion is at 41 degrees. I'm going to add 90 to that. So 41 plus 90. And if you want, you could do this to add 90 if you don't want to actually do the math like Lieutenant Fight. He never wanted to do the math, but I do. So here, I just go from here to the 41. 41 plus 90 is 131. So, at 131, that angle to the center, I draw a straight line from 131 that passes through the center. And I generally will just draw a line up to there. And that, where this intersects the this line, that is our CPA. So from this, we have all the information that we need to get the CPA. So to find the time of the so the CPA is determined by the distance, the range, and the time. So our range is straight up just going to be a measurement of distance from the center point to here. Go back to the 3-to-1 scale. This is 14,000 yards. So CPA range is 14,000 yards. And the time of CPA is going to be at, so we want to get the distance to this point. We already know that speed from before, which is 21 knots. The distance is, on the 3-to-1 scale, 16,000 yards. So you go up to 16,000. We know 21 knots. So the time the time that's due to that change is going to be through there.
Use that. So you use this to figure out some relative speed. Okay, then you figure out.
So 21 to 23 minutes. So our CPA is at 920. So it's at 0943 is our CPA. And it says, will he pass astern or ahead of you? That seems to be, this is our bearing. He's going to pass off of our port bow, so he will pass ahead of us because he's basically just cutting right in front of ours. Does that make sense? Okay, so what if this were really closer and we wanted to say what if for some reason, I mean, it wouldn't be, you would never do this, but on the test we might have to do something like this. So if we wanted to keep him out of the 15,000 yard box, normally it would be out of a 4,000 yard box or something like that. But so if we wanted to keep him out of here, oh, that's awful. This is just, I can't do this. Okay. So basically you want to keep him out of here. Gosh dang it. So we see him bearing here. So at 920 we say, sir, he's going to pass within our range. So what we need to do is make sure that our bearing keeps him outside of here. So we can either do this, or I'm sorry, we could either do this. This is more logically coherent. Which would this bearing right here? That if we took a bearing, changed our relative motion to him to keep him outside of the circle, that would probably look like a large deviation, as opposed to this. See how that lies tangent here? This is almost the same exact bearing. So what we do from there, so that would be his new line of relative motion, is this one. So in this situation, if we're going to alter course to keep him outside of our bearing, what is changing? The ER vector is changing, right? Because that's our course. The EM is going to be constant. That's what we're assuming. So basically what we do is we move this to the EM.
So now you take,
we move it here. So anywhere on this line, any new vector, ER vector, could lie anywhere on this line. So our current course is 350 true. So what we could do is stay on 350 and slow our speed to whatever this speed is on the 5-to-1 scale, or we could maintain the same speed and alter course to 6 true, or we could increase speed and alter course, or decrease speed and alter course along this new line. So choose any of those points, and that is it. Okay. How long was that?